Hello, everyone. Hope you've had a great day so far, and welcome to the November session of our monthly webinars. We're going to wait for a minute or two to allow people to join and sign in, and then we're going to start. So here's the outline and format of this training session. A quick introduction and an introduction to the presenter as well. And then we'll have the technical presentation for about 25 to 30 minutes, which is followed by question and answers for 10 minutes at the end. If you can please type your questions on the chat area of WebEx, addressed to the host, then I'm going to ask the questions from the presenter at the end. Okay, so quick introduction. My name is Ali Reza Farghani. I'm the host today, and I'm the engineering lead of Numerical Methods Group. Our presenter today is Mr. Alistair McKee, who's the engineering lead of Analysis and Applications Group. Alistair has been with Convergent for more than 6 years now, and he has a long time experience with composites in different areas, material characterization, consulting services, as well as actual production of composite parts. And Alistair is going to give us the presentation today. The title of the talk today is Cure Cycle Optimization using Raven software. At Convergent, our main goal is to help our customers to reduce the risk of manufacturing of composites. We offer a variety of products and services to achieve that goal. On the process simulation side, we have a few software products, including Raven, which is going to be used in this session today. We have Compro, that's a very powerful tool that sits on finite element applications, and our next actual session will be on Compro. We also offer LIMS that can be used for mold filling simulation and injection simulation, basically. On the hardware side, one of the examples here is the Coho. That's the gas flow and vacuum leak detection system. It can be used to detect, if you have leak in your bag, and also quickly find where is the location of the leak. Can save you hours and hours of time in finding the leak by doing the leak localization. Also, in order to use our software, you need to first characterize the materials. We offer materials characterization services, as well as engineering services, training, and consulting and program support as well. Many of the major aerospace companies are our customers and use our products and services. We also have great relationships with universities around the world, and try to be on top of what's happening in the composites world and incorporate the best models and simulation technologies in our software as well. All right, so Alistair, do you want to start?
Thank you for the introduction, Reza. That was good. So today I'm going to talk about Cure Cycle Optimization using Raven. And to get started, I'm going to talk a little bit about thermal management to give everybody a bit of background around this topic. So when we talk about thermal management, we're really looking at the entire thermal system in this context. And for composite parts, they're typically cured in an autoclave, and so we need to actually take care of that entire curing environment, as well as all of the pieces that are going in with it. So in this case, we have that soft tooling on the top, the part itself, and hard tooling on the bottom. So this would be like the bag, the composite part itself, and then whatever the mold or tool is. And we have a few different heat transfer mechanisms to worry about in this case. So we have convection, conduction, and then radiation as well. Radiation, I'll say, is one that we are not currently implemented in Raven, but that's not a huge concern with the simplifications that we made. And then the thing that's unique to composite parts is this heat generation from the chemical reactions. That's the exotherm people are probably familiar with. That's heat generated by the part itself. So if we look at the science of thermal management, and we're looking at doing a thermochemical simulation in this case, we have a governing equation, and this is really the heat at any given point. And we have a term here which is the conduction of the heat through there. And what's unique about composites is this heat generation term, this Q dot. And so this is actually a function of the degree of Keir, volume fraction, and some of the other properties of the composite itself. And then we have the heat flux into the top of the surface. And this is really our heat transfer coefficient here, and that's from the air temperature to the surface. And we have different boundary conditions that would be used in these cases, adiabatic being no heat flow in or out, but the most common would be using either convection or a set temperature. And these are ones that we can use in the analysis in Raven. And in this case, convection is a function of temperature and pressure. And that's essentially your autoclave air pressure will affect your heat transfer coefficient. And then the material properties, these are a function of degree of Keir, temperature, and volume fraction as well in this case. And that is, volume fraction comes into it because the fibers are typically inert in composite materials. So it's really the resin that is curing in this case. Now, one thing we need to keep in mind that you do need to keep both the part and tooling. These do need to be accounted for in the simulation to be the most accurate. But certain things like the effects of the bagging material, the substrate, and other details, they can actually be smeared or calibrated in for numerical efficiency. And you'll see a little bit of that as we go through. And just to make sure everybody has the full background here, when we talk about a Keir cycle, this is the temperature and pressure that we apply usually it's what we program the autoclave or oven for. And there's usually some bounds on that. And so we might have an upper and lower heating rate, hold, temperature, max and min, and all the way through. And this really bounds the acceptable criterion where the part has to go through this. These are very common in aerospace and other industries as well, to be specified and really tightly controlled. And so if we're going to do a simulation of a composite part, we have our Keir environment here, and we have this part laid up on this tool, and we're going to apply this. And what we're going to do with Raven today is look at how we can actually see the result of this applied temperature and how that will affect then our part temperature. So this is incorporating all of those equations that we talked about earlier and giving us the result here of what should happen in our part. So the example we're going to talk about is this composite wing spar. So this piece right in here, especially at the root, is a very thick, over 200 plies of prepreg. This, in my example here, it's going to be 1.5 inches at 38 millimeters. And we have a Keir cycle specification that has been given. So this is just a typical example, 0.5 to 2 C per minute at the ramp rates that are acceptable, and then hold temperature. We need to get to 180 C for 2 hours, and we have plus or minus 10 degrees C on that. But what we really want to do in this example is going to minimize that total cycle time, and that's really what we're going to try to optimize here. And so the method we're going to use is the 1D analysis within Raven. And so this, if you're familiar with the webinars, we've been using this for different parts. In previous ones, we've been looking at different thicknesses of parts. In this case, we actually are just going to look at the one thickness, but we're going to work on or optimizing that Keir cycle that we're applying. So we're using this 1D drill through, and this is essentially just a cross-section of the part. And this is a really good approximation for composite parts, unless you're right near the edges. And so what are the assumptions that we actually use in this? And it's that there's 1D heat flow, and so there's no heat transfer in or out of the sides of this. And this is typically true for composites, and again, unless you're near the edges where you will actually have heat transfer on those sides. And then we can only, in Raven, we can only apply a single heat transfer coefficient value. We can apply a different one top and bottom, but we can't have it variable in the current version throughout the cycle. That's not a limitation if you move into Compro and other software. And so this is the example that I'm going to go through today. So in this case here, I'm going to define what we have as our part material. I'm using Hexcel 8552 AS4, and then we're going with the thickness, 1.5 inches, 38 millimeters, and the tool, I'm going to use a composite tool as well, and this is about a half an inch, 12 millimeters thick. And what we do is we define this stack up within Raven, and now I have different cure cycles that I want to try where I have these criterion. So I have a minimum and a maximum ramp rate. We actually have a maximum temperature criteria. That's the most likely one. And we can keep adding additional criteria onto this. For example, the hold time at 180 is one that would be on here that we could include. But for simplicity today, I've just included these three, and then we'll talk about other ones that we could look at. And at the end here, what we're going to look at is this cure cycle time, so we can compare different cycles. I've got actually 5 cycles we're going to go through today. Okay, so at this point here, the goal is to minimize that cure cycle time given these constraints. And so I'm going to jump into Raven so that everybody can see this. Here we go. Let me just make sure we've got this side here. So we go side by side here, so hopefully everybody can see what's going on. So what I've got here, Raven, the latest release version, 3.11.8, and I'm going to use over here, if we come in, and there's a few different areas you see around the data tree, which we'll see actually populated as we go, report window, and this is the main analysis window. And you see over here there's some different tasks, and I'm going to use this 1D thermal profile study. So this brings up the interface here, and so if you've been following the webinars, you'll be pretty familiar with this, but I'm going to define our stack up here. And so we first need a boundary condition. This is the top, and I'm using heat transfer coefficient, quite a high value here. This would be, and if you look at the tool tips, there's some typical values here, and this would be a very high one for an autoclave, high impinging airflow. Now I'm going to give a material. We need to actually choose which material this would be, and in this case here, I'm going to come down and pick out it's Hexcel 8552. I'm using our open literature model in this case. And we define the thickness. 8.1 I have here, and that's all we need there for now. We're also going to define a tooling material, so I add another piece to the stack here, come down, choose from the tooling nominal composite, and we have that thickness at 12.7, that's a half an inch. And at the end, on the bottom here, I'm going to need to define another boundary condition. This is our heat transfer coefficient, and I was using 60 watts per meter squared Kelvin here. And the last thing I'm going to do, and this is a bit of a convenience thing, I haven't been doing it in some of the previous ones, is add a datum point. And so what is this? If I add this in, you can see this option down here. There's a heat transfer coefficient, a set temperature, or a datum point. And this really just gives us what the Z measurement is of 0. And I like to put it right here on the bottom of the composite. And that just means that when you look at through thickness locations, you don't need to worry about subtracting the thickness of the tool. Everything is from 0. So that's just a nice convenient thing. Now we need to define a cure cycle. So what I'll do is open this up here, and if I use one of these default ones, these aren't exactly the one I want to start with here, but these are built into each of the material files, and we have different upper lower bounds. So I'm actually going to start with a custom one. If I drop over here quickly and go to this next one, this is what we're going to start with. Cure cycle number 1 is this baseline cycle, 180 Celsius at 1.5 C per minute and hold for 2 hours. Sounds like a pretty typical cycle. So I need to actually create a custom cycle here in Raven. It brings up an editor here where we will start with a ramp to the hold temperature, 180 C, at it turns out to be the default, 1.5 Celsius per minute. Hold for 120 minutes, and then I'm going to ramp back down to 20 Celsius here, room temperature, and I'm going to use a fast ramp rate on the cool down here. So this is now defined that cycle, and we could actually call this here for good bookkeeping cycle 1, baseline, and we're going to say OK. So that has now defined that cycle, and we're actually applying this for the top is going to use this main cycle, which is defined in this box here. The bottom is also using that main cycle. If, for example, you needed to define a different set temperature, for example, you could actually define a top and bottom separately through that. And this is everything that I need to now actually run a simulation. So we're going to say OK, and Raven only takes a few seconds to run one of these simulations. This is one thing that makes it so powerful that you can do this very quickly. And so this brings up our window here, and we've got by default a plot here which has a through thickness. We got the top, middle, bottom stack up of this. And I'm going to hide a few things for clarity here. The nominal composite I'm going to just hide, and actually the bottom, which is the same heat transfer coefficient is at the applied temperature. I'm going to hide that as well. And so we end up here with a plot that looks exactly actually like I have done here. But the first thing that we see is that this exotherm is going to be most likely problematic. And so if you were to actually parse this, what tools would we want to use here? And so I actually need to go in and check a few things. So first off was the ramp rate. So we're going to say, okay, check this ramp rate here. We've got a slope. So that's within the specification 0.5 to 2. So that's good. I can also check the ramp rate here that we have for the part. That's also right in line with that. And then we're looking here at this max temperature. And so I would use one of these define local maximum probe tools here and select a couple of points there. And now we've got that local maximum here. The other thing that we're interested in at the end was this total cycle time. And so if I wanted to pick that out of here, I can read it off the axis here. We can zoom in and such and get it, but I can also probe this. And it gives me the time. Now it's telling me the temperature at that time. I can actually double click on this and customize this. So this would be cycle time, for example. And there are a few different options in there. This is going to take the x-axis value and the x-axis units it's going to display, and you see what it shows now. Cycle time, 258.8 minutes. So that's the first one cycle that we have here. Now, if I come back to our criterion, we realize that we've actually exceeded the maximum temperature. That exotherm peak is too high. And so we can go through some different scenarios now to actually explore what we can do. So first thing we need to do is address that peak temperature before minimizing the cycle time. So the next strategy that I would employ in this case would be to use a lower heating rate. So this is going to reduce that exothermic potential, so some of the exotherm will come out as we ramp up. And so we're going to use the lowest possible here, 0.5 C per minute. And I'm going to show these examples here and then jump back into Raven for some of the end ones here. So cycle 2, now we've gone through and essentially I've edited that cycle. And we can see now that we are within specification because I've lowered that heating rate. Maybe a little bit low, all this is right on 0.5 essentially on the heat up. We've got that exotherm under control now. However, our cycle time has almost doubled here. And so this is now where we want to actually start to optimize this cycle. And so we can use a different strategy potentially to now try to shorten that time. So the goal here is still to keep our cycle time low, but reduce that exotherm, or while still controlling that exotherm peak. And one option that we have is also to try a 2-hold cycle. And so in this case, this is something pretty typical done in industry where we would introduce an intermediate hold for Hexel 8552, I think the default cycle actually has a 140C hold. And so this is what we're going to try to do to control that peak exotherm, and then we'll have the final cure at temperature there. And this, you see the cycle time is getting a bit shorter than that long hold option. And so we can see here that what we actually have done, again, we have reduced or controlled that exotherm because we haven't really exceeded that 190C. We have got the ramp rates within reasonable bounds all the way through, even in these hold section or ramp sections here. But the thing that I identify here with these circles is that we could potentially shorten this cycle time by reducing the amount of time in the lag that's associated with the part catching up to that hold temperature. It'll asymptotically approach these until the exotherm kicks off. So what strategy do we have next in our toolbox here is that we can use overshoots. And this is also something that's done in industry where essentially you intentionally ramp a little bit higher to keep the temperature difference between the part and air temperature constant. You try to keep a gradient across that, which will drive that heat transfer to keep going. And so in this case here, we can program in these overshoots. So if I was to actually go back into Raven here, if I wanted to modify this simulation, I can actually just open up the simulation by double-clicking on the gear symbol up here. And we bring this up, and we actually have the gear cycle here. So I can edit this cycle here, and there are actually options for opening a cycle and saving this out. And so I've actually, much like any good cooking show, pre-made some of these cycles. And we can load these in here, and this is the one that I wanted to actually see, and I can load that in so we can see what this looks like. And so in this case here, we're still ramping at 1.5C, but instead of going to 140, we're actually going to overshoot slightly. And in my case, I've chosen 10 minutes here, and then we're going to ramp back down. And so one question might come up is, where do we actually pick that? And I can show you how my logic would be on that. And we've done the same thing here. We'll hold for 2 hours again, go up, overshoot a little bit. And you will probably note that we are still actually increasing the total cycle time a little bit with this cycle because we've still got this 2-hour hold. Now I'm going to click OK on all of that. And what Raven will do is update that cycle and rerun this for us here. And we might have to move a few of our probes and such to reanalyze this. It seems to have picked up quite a few of these spots pretty well for us. So we've got the initial slopes. These are looking good. We've got this peak exotherms here as well. I can jump ahead with this. And you see what we've achieved with this overshoot is right in this area here. I'm going to hide the legend for us. Is essentially we want to overshoot and keep that. This is the surface temperature actually at the top of the part here is coming up. We don't want this to exceed 140 by a significant amount, but we want to keep the applied temperature coming up until the lagging TCs are really approaching that. And so that's essentially how you would tune this timing. And you could actually do this all virtually rather than trying to do trial and error to optimize that overshoot. And you can do it all here before you actually move on to a real part. And so we go in here, and this has, I'm going to zoom out a little bit so I can bring my probe, the cycle time one, we'll delete that. Essentially, we can see here we do have a significant overshoot here, and this may or may not be acceptable within certain specifications. In my simplistic specification, I'm saying this is okay, and we've got the overshoot again here, and we've controlled that. So we have not exceeded 190 Celsius anywhere in this cycle, and we're reducing that cycle time, and we can check that at the end here as well. So we're at 425 minutes. But I do see some potential right in this zone here where we can actually shorten this time as well. And essentially what we see here is that the part has exothermed and now is cooling, and so this is, there's no cure occurring here, and we want to actually try to optimize that. And so we can go into another alternate cycle here. This is cycle 5, where I've reduced that cycle time, hold time essentially in that first hold. And so what we've done is employed each of these strategies with the overshoot and a small hold with that initial hold, and then a slow ramp up to control any residual exotherm that we might get into that, that hold here. And you will note as well, I've increased the initial ramp rate up to 2 C per minute, and that's because when we've done all of these at 1 C per minute, we see that we essentially follow that or a little bit low, and so therefore we can move up to this faster heating rate, and that will save us a little bit more time as well. So if we go into this cycle, we end up seeing here that we've got the ramp rate. So yeah, we're still below 2 C, that's great. We've got a reasonable ramp rate even approaching into here, and our maximum has been controlled. And what we're effectively doing with this cycle is after the exotherm has occurred, we're following that internal heat generation. We're following that up with the Cure cycle as well. And with all of this, we're actually able to reduce that cycle time down. It's not shorter than the initial one, but it meets all of our specification requirements, and we've been able to reduce that time down here. So the way I would typically approach a problem like this is to create my table, and then we would actually go through and parse each one of these. And so I've actually pre-filled this out, and the red things are the places where we've actually exceeded, and that's in our case here, that is 190 C was the maximum temperature. So that first cycle, while being the shortest, exceeded that time. And in each subsequent cycle, we were reducing the time, or in some cases increasing it, but we were within specification until we got to cycle 5. And for any given cycle, you can keep doing these iterations, right? I've shown different examples and strategies to get there, but of course, you can actually get probably shorter and shorter for the exact process that you're looking at. So in summary, I've shown today, Raven you can use these 1D drill-throughs to quickly assess various cure cycles. And what we're looking at here is trying to control well, different strategies in cure cycle optimization. And so in this case, we're using intermediate holds or low ramp rates to control those exotherms. We're reducing the lag entering the holds, and that was using overshoots. And then once that part has exotherm has peaked, then it's sort of possible to proceed on to the next hold, and that's what I mean by following it up to the next temperature. So in conclusion, the understanding all of the total system components and how they interact is really the critical thing for a thermal management problem. Raven is a really effective tool for testing out different strategies without actually having to do the test experimentally. And you can really gauge whether or not these are going to potentially help you or not. And this is really, I hope, showing you how simulation can help optimize cure cycles, and it's really a different option instead of going to experimental trial and error. So if you have any questions, please type them into the host now at this point. And if you think of a question in an hour from now or a day from now, please feel free at any point to email us at info@convergent.ca. I'm happy to follow up with that. And I will say that the next webinar is going to be actually, we're going to skip around the holiday time, and we're going to go into January. So end of January, last Thursday in January.
Great. Thank you, Alistair. We already actually have a few questions typed, and let me start with this one. One question is that the boundary condition that you used in Raven, so you had two options of HEC versus direct application of temperature. In what situation would you use HEC, and what condition direct application of or set temperature is more appropriate?
So the part you're looking at here would be these boundary layer properties or these boundary conditions. So heat transfer coefficients are most applicable when you potentially don't know you don't have actual data to base it on. And so if you have, in this case, we need to make an assumption, what is the effective heat transfer between the air temperature and your part surface. And so you can actually lump many things into that. And so in my case, I haven't included any bagging or breather at the top. And we are essentially assuming that as part of this coefficient here. Now, when would I use a set temperature? And so in case of a set temperature, it will follow exactly along this cycle right on the top of that surface. So you will not see any lag between these. And that's usually most applicable when you have thermal data from an actual cycle. And so if you have temperature data from an autoclave cycle, you can import that in as a cycle here. Cycle from data, which is grayed out because I haven't imported any. And in that case, we can actually use that right on the top surface. And another application for set temperatures is also in something like a heated tool. So a mold temperature for cartridge heaters, or a platen temperature as well. If you expect that boundary, the top of the laminate itself, is going to be set to this temperature, then you can go from there.
Yeah. So HEC is used when you have convective heat transfer and you know the air temperature.
Yeah.
Whereas if you know the surface temperature or you have cartridge heaters, you can use the set temperature.
Yeah.
Yeah. All right, so next question. I think this was discussed before as well, but say if you have different thickness profiles. You have a thick part as you showed here, but in some areas you have a sandwich, in some areas you have a sandwich structure. How do you deal with that in this optimization workflow?
So if you've been following along on the webinar series, some of the previous ones were actually how to deal with sandwich structures and then different thicknesses of laminate. So essentially talking about this 1D drill through. And really what you would need to do is do this simulation, but also change your stack up to the different 1D drill throughs that you would see throughout. So in this case here, once I've optimized the cure cycle for the thick laminate portion, if I had a sandwich portion of this part, I could then also do that same criteria on that. And so it does get more complicated as you'll need to actually check more cases. And really what it does is it expands your table here. Not only do you have different cycles to try, but you have different analysis definitions essentially, so a different stack up would be required. And you can do that within Raven, and you can actually share a cycle between. So if you had, say, 5 different cases of your laminate, then you can actually apply the same cure cycle to all of them. And that is using, in here, we can share a cycle with another analysis in here, so you can actually propagate that through relatively easily.
Great. All right, let's see. The next question is about other constraints. So we talked about the thermal constraints in terms of ramp rates and peak exotherms, but what if something like consolidation is also important for you to achieve a good consolidation? How can you consider that and bring it into your constraints as you apply it?
Right, so there are many different properties that we can look at, and I've only been showing the temperature. Of course, if I want to add a new series to this plot, we bring up this here, and we actually can see, I just have to pick a location within my laminate. I'm going to pick about the middle there, and you can actually see that there are many different properties calculated throughout this. And so Raven doesn't directly give you a measure of consolidation. However, flow index is one option that we can use. And so we actually, it's reported, I'm going to actually go, I was looking for viscosity. And so flow index is something that's used, and so I'm putting viscosity on here, and it's essentially a measure of the area over the viscosity curve. So it's a measure of how much time you have at a low viscosity, And this is allowing things to flow, so consolidation can happen, and gases can escape, and resin can saturate into all the different areas. We actually see, I'm going to bring this window up here at the bottom, and so when you run the simulation, I see why we don't have it here. In the 1D simulation, it doesn't display that. So given a 0D simulation, we should be able to see that in the report window. I'm going to share a cycle here with the other analysis. Right here, it gives us this measure. It's the flow index, and that is the area over that curve. And we can actually add it here now. So we have viscosity, and I should have, it's just buried in here, resin flow index as well. And so this is another way to compare two cycles. And typically things with a higher flow index would have better consolidation.
Gives more time.
More time at a low viscosity for resin to flow in. And of course, the topic had come up in that question about other properties and something like degree of cure. So I didn't focus much on the time at temperature here, right? We've assumed that this is going to have 100 full 2 hours at 180 C. However, what you really should be concerned about is what is your final degree of cure, or maybe another thing like TG. And so that's something that we can easily plot here for any of these cycles, and we can see that we've achieved a minimum degree of cure. That's just not often specified within the cure cycles in specifications. It's actually, they've designed that cycle to ensure that you get to a appropriate degree of cure. And one way that we would approach some problem like that, if you are not beholden to a specification exactly, is to define what is the minimum properties based on degree of cure, and then optimize to at least achieving that as a criterion.
Great. All right. One last question that's asked here is the effect of substructure in your tooling. How can you bring that in a 1D simulation? So in a 1D simulation, you're representing your tool as a constant thickness, basically, right? How is it possible to somehow incorporate the effect of substructure?
Yeah, so the typical way, and so what you're referring to there is this structure underneath, and you can see it here in the picture as well. So this whole substructure, and essentially what is going to happen there is it's going to add thermal mass to the bottom, to that tool surface. And so one way to incorporate that into it is actually to artificially thicken the bottom, the tooling thickness there, and it would be an equivalent thickness to what the thermal mass with that understructure. It's particularly applicable for metal tools because they have good conduction, and typically good conduction between these. The surface composite tools might be less of an issue. The other place that also a consideration is that the airflow is typically much worse underneath, and that's why we often have a lower heat transfer coefficient. It's because the airflow is much worse on the bottom side of the tool.
All right. Great. I think that was all the questions that we had from the participants. Yeah.
Okay. Well, thank you for joining us today, and we will be back in after the holiday break here, and at the end of January, we're going to be talking about introduction to process simulation with Compro, and I think there'll be a lot of interested people on that one. Thank you.
Happy holidays, everyone. Thank you.